Welcome to this new series of videos in this channel, which are Structural Dynamics Fundamentals. The serial number of this current video is video DIN 1. DIN stands for Dynamics. So more videos shall come on this structural dynamics gradually. Let us study the symbols that we shall be using in these videos. M equal to mass of the system, K is stiffness, C is damping coefficient. And you can have the corresponding matrix forms of this is mass matrix, stiffness matrix and damping matrix. Cc is the critical damping coefficient, T equal to time, J equal to critical damping ratio. Ut is the displacement in the direction of the motion. U dot T is the velocity in the direction of the motion. U dot T stands for du dt. U double dot T is the acceleration in the direction, which is equal to dt d2t, which is equal to d2u dt square. Ft is the dynamic force. Some basic concepts and terms let us understand now. One is the dynamic force and static force. What is the difference? A dynamic force is a magnitude, direction and point of application which change with time. What about the static force? Static force has magnitude, direction and point of application which do not change with respect to time. Let us take example. If I say F equal to 10 kN force, then F is a static force. But if I say Ft equal to 10 sin omega t kilonewton, it is a dynamic force. As the time changes from 0 to any value, the Ft also will be changing. That's why it is called dynamic force, that force that which changes with time. The magnitude changes, the point of application also may change, and the direction also changes. Here is an example. We have taken a force whose magnitude is 10 kilonewton, and it does not change with time. It is 10 and 10 only all the time, so it is static force. On the other hand, we have taken Ft equal to 10 sin 1t is a force which changes with time. So when t equal to 0, it is 0. At t equal to certain value, it attains a peak, and then it again falls and again comes to 0 and so on. So it is changing with time. Its direction is also changing. Here if the direction is on the positive side, then here in the second half of the loop it is on the negative side. So direction is changing and the point of application also may change. So it is a dynamic force. Let us take another example. Ft is the vertical axis and T is the time axis, and the force changes like this, gradually increasing with time. So it is a dynamic force. Another, a triangular force, the force which rises then again falls in a triangular fashion, then it is a triangular force. This is also a dynamic force. Now the previous case let us take once again, where Ft equal to 10 sin 1t. So 1 is called the frequency. Let us try to understand this by increasing the frequency. Let us take is 2, frequency is 2. Then we see that the number of waves have changed. Now in the beginning, the first wave starting from 0 to peak to 0 again and negative and to 0 again, it took place about 6.7 here, so 6.4 second. So one cycle was completed in 6.4 second. In the present case, you see within 6.4 second, it is completing one cycle, then another cycle, 2 cycles. Let us take when omega equal to 3, then within the same time span of 6.4 second, it is one cycle, second cycle and third cycle. 3 cycles are completed. So that is the meaning of the frequency. More frequency, more will be the change of the direction of the force, and the force will be showing wavy forms. Let us now understand some connected values with this force. The force was 0 in the beginning, attains a peak value here, and then gradually again falls and again comes to the 0 value here. This completes one full cycle. This time taken to complete one full cycle is called the time period. The maximum displacement shown by the system is called the peak displacement or amplitude. Now let us see damping. Damping is the phenomenon where the amplitude of the vibrating system diminishes with time. The amplitude diminishes. Damping opposes the motion. That's why the motion comes to stand still after some time because of the damping. Otherwise, by Newton's first law, it would have been vibrating eternally. When damping considered in this motion, it is called damped vibration. When damping is not considered, it is called undamped vibration. So undamped vibration goes like this, where the peak amplitude remains always the same. But if it is damped vibration, then peak amplitude in the first cycle is this, first half cycle, then second half cycle it is less, next half cycle even less, and gradually it is diminishing and finally it will come to a standstill condition. This is called damped vibration. As we have said, damping is a force that opposes motion. So let us try to understand that force. Damping can be velocity proportional, which is called viscous damping. Suppose you are moving a plate in a fluid, maybe water or maybe some other fluid of higher viscosity. Then while moving the plate, you will get a resistance, which is called drag. So this kind of damping is called viscous damping, which is proportional to the velocity of movement of the, say, plate in the fluid. Fd varies as u dot t. That is, the force in damping is proportional to the velocity. So Fd equal to a proportionality constant c into u dot t. This c is called the damping coefficient. What is the unit of the damping coefficient? You change the sides, then c equal to Fd by u dot t, and it is equal to Newton by meter per second. So it is Newton second per meter. Damping can be displacement proportional. Then it is Fd varies as ut. This case will happen in case of friction damping. If you are rubbing one plate over the other, then friction damping will be experienced, and it will oppose the motion between the two plates. Obviously, the amount of force that it will be generated based on is dependent on the displacement that the plates are undergoing. Now let us take a single degree of freedom system, and we apply a displacement to the system. We drag it to the point B and release it. So after releasing, it will go to the point A again and then go to from the further side to point C, and this will continue to and fro, left and right. So we started from A, then we had gone to B, then again back to A, then to C and back to A. This completes one cycle, and this is called the time period of the system, which is the time taken to make one complete cycle of vibration. So this one complete cycle of vibration is A to B, to A, to C, to A again. Starting from the standstill position, making one complete cycle, you come back to the standstill position once again. So this is what is shown in this diagram. He started from 0, then peak value, then again 0, then negative peak value, then again 0. So those points corresponding to the vibration, the single degree of freedom systems are here: A, then B, then again A, then C, then again A. Now you see, if you take the gradient of the things between A to B, it will be positive because it is rising curve. So what is the gradient of the displacement? It is velocity. So velocity in the rising curve is positive. So velocity is positive up to point B. After B it is going down, so the gradient is negative, so velocity will be negative. So from B to A it is negative. A to then up to A to C also negative. Then again C to A, when it is moving, the velocity is positive. So you can see that the velocity changes sign at the extreme point B and at the extreme point C. This property will be utilized in studying the vibration in many cases. Cyclic frequency is the number of cycles completed per second. So expressed in F, and the unit is hertz. Angular frequency is the number of radians traversed per second. It is expressed in omega, and the unit is radian per second. Now by definition, one cycle is completed in 1 second. So obviously the frequency is equal to, and it covers one cycle in one time period t. So F equal to 1 by t. Similarly, omega equal to twice pi by t, because twice pi radians will be traversed in one complete cycle, which corresponds to a time period t. So omega equal to twice pi by t. You can make now a relationship between F and omega. So omega will be equal to twice pi F. Now for vibration to be possible in engineering sense, there must be stiffness or spring resistance in the system. If this spring resistance is not available, then it will be certainly it will be moving, but it will not be called as vibration, it will be called as oscillation. As in the case of a pendulum suspended by a thread and it is oscillating, then it is oscillation, not vibration. Stiffness is the force per unit displacement, so K equal to F by delta, or delta equal to U or displacement. So writing in the reverse way, you can get F equal to K into delta. This F is called the spring force and written as Fs. So Fs equal to K delta, the spring resistance in the motion. This spring resistance will be opposing the motion. From second law motion, the rate of change of momentum is equal to the applied force. So d dt mu dot equal to F. So m is constant, I can take it outside. So m d dt u dot equal to F. You can put Ft also because it is dynamic force. And d dt u dot is nothing but u double dot. So mu double dot equal to F. This is called the inertia force. So we are putting a suffix I here. So Fi equal to mu double dot. Now this has very high implication in vibration. Any system has a mass and the mass gets accelerated during the vibration, and because of that this inertia force will be generated. This inertia force will be opposing the motion. It will be opposite to the direction of applied force. During ground motion, inertia force is created in the system due to acceleration of the masses. Now we have got some forces we have discussed. The spring force we have discussed, Fs, and the damping force Fd we have discussed, and the inertia force Fi. And there will be external excitation force or external source of vibration, which is Ft. These forces shall be in dynamic equilibrium at any instant of time. What is dynamic equilibrium? Static equilibrium, you know, sigma Fx equal to 0, sigma Fy equal to 0, sigma m equal to 0, etc. Those things in 2D or in 3D. So what is dynamic equilibrium? Dynamic equilibrium means when a system is vibrating, no force is taken out of the system and no force is added to the system. At any instant of time, it will form a static equilibrium at that very instant of time. And this is called dynamic equilibrium. So now we can write down those forces. Inertia force plus damping force plus spring force should be equal to the applied force or exciting force. This is called excitation, Ft. So it comes to mu double dot t plus cu dot t plus k u t equal to Ft. This is called the equation of motion or equation of dynamic equilibrium at any instant of time t. So this is the fundamental equation through which you should be studying the structural dynamics. Sometimes some terms may be absent and then it will be called a particular type of vibration. And when there is multiple degree of freedom system, then M will be mass matrix, C will be damping matrix, K will be stiffness matrix, and F will be series of vectors. Similarly, acceleration, velocity and displacement also shall be in terms of vector. That we shall take up later on when we discuss multiple degree of freedom system. Now, when you take all the terms together, a right hand side excitation is present, it is called force vibration. But in some cases, suppose in the first instance we had displaced the system by a displacement and there was no other extra forces, so it was in that case represented like this. Left hand side equal to 0, then it is called free vibration. So we have force vibration where excitation exists, free vibration where excitation does not exist. Free vibration mainly takes place through displacement given to the system initially. Now we can have different types of vibrations. Certain terms we shall eliminate from the equation of motion. Now which terms cannot be eliminated must be there so that it is a vibration. Inertia force cannot be nullified, so mu double dot t will be always there. If there is no spring action, it is not a vibration, it will become oscillation or a rigid body motion. So this has to be there. So minimum terms mu double dot t plus ku t equal to 0. This is called undamped free vibration. It is free vibration because right hand side excitation force is 0. It is undamped because the damping term cu dot t is absent. Now let us take the second case when the right hand side is not 0. So it is again undamped because damping is not there, and right hand side present, so it is forced. So this is an undamped forced vibration. Let us take another case when damping is also added. Then you have three terms on the left hand side, right hand side is 0. So this is damped free vibration. Damping is there, so damped, and right hand side 0, so it is free vibration. Now if I take all the terms together, right hand side is also present, then it is called damped forced vibration. This forcing function or excitation is there, so it is forced vibration, and damping is there, so it is damped forced vibration. Now physically let us see the vibration types. It is called extensional, a spring-like things where it is extending and contracting. So this kind of vibration is called extensional vibration. We have taken a cantilever bending here, a cantilever which is fixed at the end, and the beam is vibrating under self weight shown here. Then you can have beams like this which are vibrating due to bending moment applied at the center. So this kind of vibration is possible, beam bending vibration. And torsional vibration when it is rotating like this, torsional vibration. Shear action can be there. I have put a single force here at the middle, and there are two supports. So shear force diagram is like this. So under shearing, there will be shearing vibration. This will be further clear from the next diagram. Here these things are shearing downward and laterally also this side. So it is a shearing. More clear from this diagram where we have taken a book and we are pushing the book in one side, touching at the top. The bottom of the book is not moving, only book is getting a different shape, and this is called the shearing of the book. Now if I press it on the left hand side, then the shearing will continue like this, and it will be shearing vibration. Let us see the stiffness is concerned with the different vibrations. In the axial vibration, axial stiffness given by AE by L. A is the area of section, A is the modulus of elasticity, L is the length of the system, K is the stiffness. For flexural stiffness in beam and rotation, K equal to 4EI by L. This you have studied in your structural mechanics in BTech some semesters. Flexural stiffness for beam and displacement is given by 6EI by L square. Then stiffness against column displacement, when this column top displaces, it is 12EI by L cube. L is the height of the column. Now let us see the spring mass representation. The system can be represented for our modeling purpose. Physically we have described it, it is like this. Now let us see pictorially how it looks like and how our forces are acting on the system. This is called spring mass representation diagrams. So we have taken a single degree of freedom system with mass here which moves up and down. So it is a U T is the single degree of freedom system that it is undergoing. K is the stiffness. So it can be represented here like this. Yes, in the second diagram, stiffness is shown and the mass is shown, and the mass is moving over a roller, frictionless roller. So the vibration which is vertical is analogous to the horizontal motion here. Ut is the degree of freedom displacement, Kut is the spring force, Mu double dot T is the inertia force. So it is the undamped free vibration case. Let us see now a damped case. So in the damped case, you have to give, along with the spring K, you have to show a damping here. This is a damper. It is called dashpot. So imagine it is filled with fluid and this plate is moving within the fluid. So it creates a viscous damping inside the system. So this is used in the shock absorber of say 2-wheelers, 3-wheelers and 4-wheelers, etc. And in many other appliances, the damping dashpot system is utilized. So you have the displacement component Ut, this is the degrees of freedom, and you have the mass of the system. You have the spring force Fs equal to Kut, you have the damping force because C damping is there here. So Fd equal to Cu dot T, and obviously inertia force will be there, which is Fi equal to Mu double dot T. We have not applied an external force here, so right hand side is 0, so it is free damped vibration. When you take external force here, Ft, the excitation force, Then we have UT, FS, FD, FI, etc. As in the previous case, there is the dashpot showing the damping, and the equation becomes this is the case where we applied the external force Ft. So our degrees of freedom is UT, displacement, then we have the spring force, damping force, and inertia force, and we have the spring constant here and the damping coefficient C shown by the dashpot. And the equation of motion is now mu double dot T plus UT plus KUT equal to Ft. So this is forced damped vibration. So this way spring representation will be possible also for multiple degree of freedom system. Thank you very much for coming with me up to here in this video. If you find it is useful, then please subscribe the channel, like and share the videos, and you are encouraged to put your comments and questions in the comment box. I shall be glad to answer your queries. This series of structural dynamics will continue. This channel is meant for the undergraduate students. So structural dynamics elementary part is a common part in the earthquake engineering subject in the undergraduate curriculum. When our new code will again appear, because it is now in suspended animation, it has been withdrawn temporarily, it will again come, then we shall be taking up topics from the new code once again. Thank you.